Good evening, everyone. In this video, I will continue my discussion with these class design steps. Okay, we'll be looking at reification of behavior and adjustment of inheritance. Okay, we'll be looking at these two concepts. Let us first look at this reification of behavior. We already have discussed like reification is the promotion of something that is not an object into an object. Okay, so we have discussed this when we were talking about this class diagrams. Okay. So it is about promotion of something that is not an object into an object. Okay. So we were promoting the attributes into classes, etc. We have seen. Okay. So actually, behavior, when you think in terms of, say, for example, for whatever the behavior which is existing in a particular class. Okay. Behavior is actually written as code. Okay, in that particular operation. And behavior written in code is actually very rigid. You can execute it, but you cannot manipulate it at runtime. But if you need to store, pass, or modify this behavior at runtime, you can actually reify it. Behavior perfectly fits into that reification. You can actually reify it. Okay. You reify behavior by encoding it into an object and decoding it when you are trying to run it. So that's about the reification of the behavior. We actually have done that one. I mean, like we have actually seen these examples earlier. Say, for example, let's go with this ATM case. Transaction, we actually has seen it as an action. Okay, transaction is an action actually. So it could be withdrawing the money, or the depositing the money, or transferring funds between accounts. But actually, what we have done is like during the design stage, we actually promoted this transaction, which is actually an action in some sense, like the behavior, to a class actually. We promoted transaction to a class so that we could actually describe it. Okay, and if that is the case, if transaction has become a class, okay, for us, all these methods, whatever the functionality that we needed, okay, we need it routine. Okay, it's an operation there and can easily be obtained by traversing the class model. Okay, so that's how like we were actually using the reification method. So behavior itself can be reified. Okay, that's about reification of the behavior. Now let us move to the next topic, adjustment of inheritance. Okay, as class design is actually progressing, we can often adjust the definitions of classes and operations to actually increase the inheritance. Okay, so I mean, like we have seen several steps in which like we have been adding methods, we have been adding classes, and then like we have actually reified the classes. Okay, so operations into classes. Okay, so we have done, I mean, like during the design stage, okay, both at class design and also like the system design. Okay, so we have been actually thinking about adding further classes, isn't it? So basically, like when we keep on adding these classes, okay, we can actually adjust these definitions of the classes and operations to increase the inheritance at later stages. Okay, when we are doing this sort of design. Okay, we have to perform several steps for that one. Okay, the first one is rearranging the classes and operations to increase the inheritance. What it is, we'll be discussing in the coming slides. Okay. Then the second one is like abstract common behavior out of groups of classes. And then like the third one is we can use delegation to share behavior when inheritance is semantically invariant. Okay, let us look at all the three of them one after the other. First, let us look at rearranging classes and operations. Sometimes actually several classes define the same operation and can easily inherit it from a common ancestor. Okay, because now that you in the class design, like you have added several classes, okay, several new classes. Now you actually go and check the class model again, and then you can actually observe like some of these classes, several of these classes, you can actually define the same operation. So basically, like you can actually put that operation into a common ancestor and have an inheritance relationship. Okay, so that is a very good way to do it. However, the point is like if the operations are pretty straightforward, okay, you can actually do that one very easily. You can identify that. Okay, but more often, what happens is like these operations are similar, but they are not exactly identical. Okay, Then what we have to do is like we have to actually adjust the definitions of these operations so that we can cover them with a single inherit operation. Okay. Once again, remember that they are almost similar, but they are not exactly identical. But if we really remember what inheritance is, all operations must have the same signature for the inheritance to work. They need to have exactly the same signature. But if you look at the operations in different classes, they look similar sometimes, but may not be exactly identical. I will be giving some examples, okay, immediately on the next slide. But remember that one. Then we basically have to adjust the definitions of the operations when they're approximately similar, make them identical, okay. Or like we have to adjust them, okay. How we adjust them, we'll see examples, okay, in the next slide. So we have to adjust these definitions of the operation so that we can actually cover them by inheritance. Let us look at that. So there are different adjustments, okay. So using which like we can actually increase the chance of inheritance for particular operations. Okay. The first type is like operations with optional arguments. Okay. Say for example, like we can align the signatures by adding additional optional arguments that can be actually ignored within the implementation. Say for example, like now you have a say for example this a monochromatic display. That means like it is not colored display. Okay, and then like there is a colored display. Now if you have a draw operation on a monocolored display, it don't need the color parameter. But the point is, but it can actually accept the parameter, the color parameter, and it can ignore it for consistency with the color displays. Then basically like what you have done is like you have aligned the signatures of both the methods. Okay. Originally like you don't need the color parameter for this monochromatic display, but then like add the color parameter. What happens? Okay, nothing will happen. You will have for the color display like you will have a method with say for example three parameters. The third parameter is the color. Even for the monochromatic like also it may have originally two parameters. Okay, but then like make the color as the third parameter, but within the implementation don't use it. That way like you have these two draw operations, you can actually have inheritance hierarchy and then like move it into a upper level class, super class. Okay, that is one approach. Then the second approach is second adjustment that is possible is operations that are special cases. Okay, some operations may have fewer arguments because they are special cases of more general operations. Okay, say for example, you want to append an element to the list. Okay, appending an element to a list is like adding that element to the end of the list. Okay, so basically like that's it. So basically like if adding okay an element and then like if there is an index, add this particular object at the index 2, add this particular object at index 5. Okay, so that add has this basically the object which you want to add and then like the index. Whereas like if you define another method which is append and then like its purpose is like say for example go to the end of the list and add it. Instead of appending that one, you can actually put like add okay that particular object end of the list. Okay, say for example get the length of the list and then like add it at the end. So these two operations, this operation okay appending is actually a special case. And since it is special case like you have lesser arguments because the index is the one which you are not putting in because it's a special case. So in such things like you actually implement the special operations by calling the general operation with this additional parameter value. That's all. Okay. That way like you are again like you are adjusting these operations. Okay. Of course, so that eventually you can actually drag them into inheritance hierarchy. The next adjustment possible is with inconsistent names. Okay. There can be times like there are similar attributes, they're in different classes, but they may have different names. Okay. Then basically the point is like give all the attributes the same name. Okay. If their behavior is the same, okay, and move them to a common ancestor class. Also watch for similar operations with different names. Okay. So this is pretty much possible. I mean like you have been adding further new classes, new operations into this during this class design. Okay. So then obviously you may find this sort of inconsistent name coming here. Okay, so we have to basically address that one. Then there can be irrelevant operations. Irrelevant operations actually come something like this one. There can be several classes in a group may actually define an operation, but some others may not. Okay. Uh, Let me give you an example. Okay. So, for example, like we have earlier seen like the figures, geometric figures. If, say, for example, if there is square, if there is a rectangle, blah blah blah, everything else, rotation, if they have a method, okay, it is meaningful for them. But for a circle, rotation has no meaning. Even if you rotate by a certain angle, still the circle is the same. Okay. Now, if you define like say for example several classes and then like several methods there. Okay, so for each and everything, okay, rotate square, rotate rectangle, rotate circle. Okay, circle will not have rotate a diamond or whatever it is, rhombus. But then like say for example, why don't you basically put it into a figure and put the rotation there as a method, an operation. Define the operation on the common ancestor class and declare when you come to this sort of and then like have all of these figures and subclasses of this common ancestor class. And for circle, like you have an empty implementation. You had an perfect inheritance hierarchy achieved. Okay. So you can think like that one. Actually, these are some of the adjustments that are possible to actually increase the chance of inheritance. That's about first thing. Okay. So then now let us look at the second one, abstracting out common behavior. Okay. So we will not recognize all the opportunities for inheritance during analysis. We came to this design from analysis. During the analysis itself, like we were trying to find some sort of inheritance. Okay. Both in domain analysis and also in the application analysis. But still we may miss something. So during this sort of class design, it is worthwhile to re-examine the class model looking for commonalities. Okay, we may miss something. Okay, during the earlier step also like we have already looked at it, but then like we were actually trying to match all the operations and everything and then like adjusting those things and so on and so on. But in this case, like let us try to relook at them, re-examine those class models, okay, looking for any commonalities. Why we are doing all this thing? Because like during the class design and all the things, we have added a lot of other classes and operations during this design step. Okay. Of course, when there is a common behavior among the classes, create a superclass. Okay, create a common superclass for the shared features, and leave only the specialized features in the subclasses. And this is how like you should actually have this sort of generalization of inheritance, which we have been discussing throughout this course actually. Okay. This transformation of the class model is actually called abstracting out. Okay, abstracting out a common superclass, okay, or common behavior. So the most encouraging thing here is like generally like you basically have abstract superclasses. By having this sort of abstract superclasses, okay, making the superclasses abstract, you can actually share them, you can reuse them. In addition to that one, they actually improve the extensibility of the software. For example, think about like say for example today you try to use an exact sensor for taking the temperature or something. You can put the exact sensor and then like use it in that particular application. Rather like abstract a sensor, okay, at higher level, and then like implement it, okay, using the particular sensor whatever you have, and then like do it. Then the point is like tomorrow if you want to change the sensor, you don't have to change the main structure. The abstract is still the same. The general sensor actually works. So you just take this subclass and then like replace it with a different subclass which is specific to that particular sensor. Have it implemented, and then like your application runs perfect. So basically, like extensibility is perfectly very good for software products with having these sort of abstract superclasses. We of course discussed these things when we were discussing about the class models. Now the third step here is using the delegation to actually share the behavior. Okay, so this is all about improving inheritance. Okay, so this is one of the steps of this class design. Okay, so the third step in this one, okay, in this part is using delegation to actually share the behavior. Okay, Inheritance actually is a mechanism for implementing generalization. So we discussed about generalization. Inheritance is a way to implement that generalization. So that means like the behavior of the superclass is actually shared by all its subclasses. And sharing of the behavior is justifiable only when true generalization relationship occurs between the subclass and superclasses. Okay, so the subclass is actually a form of the superclass. What does it really mean? Operations of the subclass, okay, that override the corresponding operation of the superclass must provide the same service as the superclass. If the superclass is providing some sort of service, so the subclass should also be like, say for example, provide the same service actually. Say for example, if the figure actually provides a rotation, the class which is actually it's subclass. Okay, say for example, in this case like circle or like square. Okay, if the figure is actually rotation is the operation, so even these actual figures should also have the rotation. It is not like you cannot move these objects. Okay, so then it is like completely behaving differently. But sometimes programmers actually use inheritance as an implementation technique. They have no intention to basically of guaranteeing the same sort of behavior. Okay, so this is called inheritance of implementation. It happens in certain cases. Say, for example, there is a class which actually has a method implemented which has some behavior. Tomorrow, like you basically are developing a completely different class, okay, and you basically want to reuse that operation which is existing in class A, for example, class B is there, okay. Then what generally the programmers will do is like, say, for example, they will make this class B inherit class A, and since you have that particular method, okay, you can directly use that method in this class B. That's an implementation advantage they are seeing about it. But what happens if this leads to much bigger problems actually? What happens because like in class B, you only wanted to inherit this method. Okay, this is the one which you want to reuse. But the point is like all the other methods like what class A has, you are actually inheriting all those operations. And this is all unwanted behavior. And probably like if you don't design the class B, and then like programmer may accidentally use something else which you are not intending to use. Let me try to give an example. In those cases, inheritance by implementation is bad, and that's where like delegation actually comes into picture. Let me try to give it with an example, discuss that with an example. So, see this one. Assume like there is a list class which is already existing. List class has, say for example, you can actually add elements to it at a particular index, okay, or like remove elements. You can actually go to the first, you can go to the last, okay. So all these things like you can do on the list. Now tomorrow you want to basically implement the stack behavior. Okay. So stack, you know about the data structures, you will be basically pushing element, okay, and you will be popping out. Now what somebody can do is like you basically can take the stack, okay, make it inherit the list, okay. In the push and pop operations, what you can do is like say for example, if you want to push an element to the stack, what you can do is like make the take it to the end of the, okay, so basically like end of the list, that is last, okay, get the last, and then like you add it there, okay, you inherited, so you had the methods and then like you directly are using them, okay, in the stack class. Similarly, like if you want to pop, you go to the end and you basically remove that, go to the last and then like remove that. Perfect. I mean, like in terms of the implementation, this would be very good. You had extended, you had already the list operations are there. Okay, so it is very easy for you to do that. But the problem is by accidentally, like if the programmer actually uses an add method somewhere, because like that operation is actually there for you to use in the stack class. And if you use, say for example, add or remove method, the basic idea of the stack data structure is completely lost. Somewhere accidentally in the source code, okay, by using this stack, okay, so basically like he added an element. Push and pop, it should have only that one, but rather like you removed an element somewhere in the middle or like you added something. The stack behavior is lost. How do you handle such situation? So in such cases, like inheritance is not a great idea actually. This is basically like implementation inheritance. Okay, this would be a bad design. So what you can actually do is you can actually have a delegation. Okay, so basically like what you are doing is like you have an aggregation. Okay, so that means like you have the stack. Within that stack, like you basically have a list. Okay, which is the actually body of all the elements. Okay, have it as an attribute, which is a private attribute, which you cannot very change it from outside. Okay, and to that one, like basically like once you have the push operation implemented here, go to that particular list. Okay, so go to the end and then like add anything. Similarly, like go to the for pop, go to the end and then like remove. Go to the last and remove. Now here, like you cannot directly change anything, okay, from outside to this particular stacks list, okay. So in this sense, like basically, like instead of inheritance, we will be using the delegation, okay. So this is also the part of the class design. So basically, like we are trying to improve inheritance. First thing is like try to see like where is there anywhere the chance to basically have more inheritance, okay, by looking at these operations and adjusting them. Okay. But even of course, like if most often like you are trying to make it abstract, okay, abstract superclasses. But the point is like always inheritance is not the only solution. Okay. So for example, in these particular cases, okay, so the delegation is a very good approach. Regarding the reference is concerned, okay, so we are still in chapter 15 of object-oriented modeling and design with UML, Michael Blaha and James Rombo. Thank you very much for your attention.